Hello everyone and welcome to another video on Nowhere You There Is. This is your host Mahmoud Nowhere. Today we'll be covering physics on electrostatics and magnetism. We'll be speaking about the electric potential energy, Coulomb's law, and magnetic fields. So stay tuned. Please don't forget to like, share, and subscribe, and leave any comments. And if I do make any mistakes, do correct me as well. And shall we get started? So, the unit of charge for an electron is 1.6 times 10 to the power of negative 19. This is really significant to know because what we're dealing with here is charges, so protons and electrons. So it's really significant to know the unit charge of the electron. So protons and electrons have the same amount of charge. Um, in a conductor, charges distribute approximately on an even surface, right? But in an insulator, charges will not easily distribute over a surface. So in a conductor, for instance, a metal, they will easily distribute over the surface, but an insulator, wood, they won't be able to pass through. Coulomb's law basically states that if you have two charged objects, the larger the charges on the object, the greater the force of attraction or repulsion. However, if you move the objects far from each other, the force of attraction or repulsion decreases rapidly. So this is represented by K, which Coulomb's constant, is 8.99 times 10 to the power of negative 9 times charge 1, Q1 times charge 2, and then divided by R2, which is the distance between both charges. So for instance, here we got two positive charges, or like two protons, for instance. They repel against each other, so Coulomb's law can also calculate the force of repulsion between them. But here you got a negative and a positive, calculates the force of attraction between the charges. Next we got electrical fields. So these are electrical fields, and these surround the charges. They exert force on other charges. So for instance, you see for instance how positive exerts a force on a negative charge, and kind of tries to pulse it in. Or like electrical fields are surrounding the charges as well, and for instance positive charges will go in the same direction as the electrical field, but negative charges will go in the opposite direction to the negative field. So the electrical field is represented by K times Q divided R2. So K is Coulomb's constant times Q, which is the source charge, right, divided R2, the distance between charges. And then electrical field is created by a positive charge. It extends in the directions away, but electrical field created by negative charge is inwards. So that's what I want you to kind of take. Electrical fields with a positive charge kind of like spreads out there, kind of goes with the direction of the electrical field, but the negative charge kind of goes inwards towards the charge. That's how the electrical fields works in the positive and negative. When two like charges repel, we calculate the electrical field, so KQ divided R2, between the source and the test charge. Next we have the electrical potential energy. It's so U equal K, Coulomb's constant, times Q, the source charge, times Q, which is the test charge. If the charges are alike, so positive and positive, for instance, it's positive. If the charges are opposite, so positive and negative, the answer is a negative. So the electric potential energy is a like a form of potential energy that arises due to the interaction between charged objects. It is the energy possessed by a charged object by virtue of its position relative to the other charged objects in the electrical field. It's basically the work necessary to move the test charges to a point in the electrical field. For instance, you got a negative source charge and a positive test charge. They attract each other, alright, and the electrical potential is negative because they're opposite, and the closer they get to each other, alright, the more stable they will be and the more negative they will be. The electric potential equation is kind of similar to Coulomb's law, except there is no r to the power of 2. And then next you got what we call electrical potential, which is a scalar potential. It's also known as voltage. So the scalar potential describes the electrical potential energy per unit at a particular point in the electrical field. It's defined as the amount of work required to move a unit positive charge from an infinitive distance away to a point in the electrical field without attraction. So ratio of the magnitude of the charge's potential energy to the magnitude of the charge itself, and V is equal to K, the Coulomb's law, times Q divided R. It's kind of similar to potential energy, except here there is no test charges. So for a positive source charge, if Q is positive, then the V is positive. And if negative source charge, then V is negative. And then in order to know the potential difference, it's equal delta V, and then VB minus VA. So you got two different electrical potentials, and then it also can equal to WAB. So W is the work, and then A times B divided by the test charges. So the work needed for the charge to move from point A to point B. If so here we got two potentials. We got the positive charges. The positive charges move from a high potential to a lower potential energy. All right, and it basically goes VB minus VA, and it's negative, and work needed is negative, and it has low electrical potential. So with positive charges, it's negative. It moves from high potential energy to low potential energy and becomes negative. All right, it's kind of like how would I say it? So let's say you can kind of make a resemblance with electrons moving from a higher level energy in like an atom's orbit or shell to a lower one. For instance, moving from a what do you call it? Like a level 3 or a third shell to a what do you call it? To, for instance, the first shell. So for instance, you got here. You're here in the first shell, and then here you got like, so the electron goes down, and then it's a negative. It's negative. Then you got the negative charge. It moves from low electrical potential to a high electrical potential. You kind of need energy for that. You need to put an energy for it to move from low to high. The WAB is positive, and I think this is a mistake. It's supposed to be WAB is positive, and there is high electrical potential. So mind me for that. Next we have equipotential lines, and these are lines on the same orbital as the same potential, which is 0. So in order to calculate the difference between the points, it's delta W equal negative charge times delta V, and delta V is basically VB minus VA. Sorry, VB minus VA. My bad. So it's negative Q times VB minus VA. Next we have electrical dipoles. So with electrical dipoles, in order to calculate them, these are the Coulomb's constant times Q times D divided R2 cos theta. Alright, and it could also be K times P divided R2 cos theta. So K is in all of the electrostatic and magnetic equation. It's really significant to know it. Alright, and then the magnetic field is measured in Tesla when T is equal to 10 to the power of 4 Gauss. Paramagnetic materials is basically will become weakly magnetized in the presence of a what do you call it? An external magnetic field. It's unpaired electrons, so electrons that are like this, they're unpaired on the subshell. And unpaired electrons have no net magnetic force, such as copper and gold. And then you got diamagnetic material, atoms with no unpaired electrons and have no net field. They are weak antimagnetic and repel by magnets. These are the diamagnetics. And then lastly, you got ferromagnetics, and these are unpaired electrons and no net charge, and will become strongly magnetized when exposed to magnetic fields such as iron and nickel. And these kind of look like this. Next, we have a calculation of the magnetic field. So magnetic field can be calculated for either circular or long and straight magnetic field. So with the long and straight, it's basically B is equal to the coefficient here, 4 pi times 10 to the power of negative 7 times current, and then divided 2 pi r. Alright, but for the circular loop of magnetic field at the center, B is equal to the same coefficient, 4 pi times 10 to the power of negative 7 times current divided 2r. The only difference between them, so the difference between the circular and the straight is the pi. Straight has pi, circular doesn't have pi. And then there's the magnetic force when charges move in the magnetic field. Alright, so in order to calculate this, for instance, let's here look at an example. Okay, you have a proton here and you need to calculate the magnetic field of this charge. Alright, so we say we're given B is equal 5T, that's the magnetic field, times Q, the charge. We said the electron charge is 1.6 times 10 to the power of negative 19, and then here they're given the V, and the V here is equal to 2 times 10 to the power of 6. But how do we get the theta? Alright, so you need to do the the right hand technique. Alright, you need to see if your thumb indicates the V, and then the B, the magnetic field is indicated by your fingers extended, and then your palm is the kind of the force coming out towards you. So that's how you calculate it. And then basically the angle of the theta is between B and V, and because they're perpendicular to each other, it's 90 degrees. And then you multiply that, and then FB is equal to 1.6 times 10 to the power of negative 12. And then you have magnetic force on the current carrying wire. So FB is equal to the current times length times the magnetic field, and this is sin theta. Alright, and that's it. Please don't forget to like, share, and subscribe, and let me know if you have any questions.